Thank you very much for the introduction. Today's session, or especially this session, focuses on AI and brain-related data. And we have two very interesting tandem lectures on this topic. The first one is a very interesting tandem lecture between a PhD student in the field and a very senior CIO in the field, senior not in age, but has been in the field for a long time. I would like to add to this. Paul Triebkorn, I hope I say that correctly, is doing his PhD studies at the Institute of Neurosciences de Système at Marseille University. And he participates in the prospective clinical trial EPINOV, and is also active in the Human Brain Project, where he works together with European research groups to further develop methods and algorithms for high-resolution models to improve predictive performance. Steven Vermeulen is a CIO, so Chief Information Officer of EBRAINS, and he started as a scientist, but has a very wide field of interests, including technical software management and marketing and sales. And I would like to welcome both speakers to their tandem lecture.
Thank you, Henry, for the kind introduction about my age. And thank you for Sharkov in the organization and Lisbeth also for inviting us. I look very much forward to further conversations because I'm here to actually introduce eBrains to you, and it's impossible to do it. Kim, sorry, I cannot do it in half an hour. But we'll give you a couple of touch points that help in the discussion that we will have during the coffee breaks and during the lunch and the rest of the day. And I'm joined by Paul, who will actually do all the detailed work. So, talking about eBrains, we obviously need to talk about what is eBrains. Am I on this slide now? Okay. What is eBrains and where does it come from? eBrains is a result of the Human Brain Project. I think most of you will have heard about the Human Brain Project as a flagship research project, actually, that has been actually going on for close to 10 years now. We still have 1 year to go. And in that project, a large part of the digitalization of neuroscience, as I would call it, happened. Not because of the project, not necessarily because of the project, but definitely there was contribution, and we have implemented certain infrastructure that as a result of that. And this is kind of what eBrains takes forward. It's not the only thing. It's not purely we take forward the infrastructure. It's also the cooperation. It's the consultation and the touch points between the technical side of things, the same as we have here, between technologists, data scientists, and clinicists, scientists, neuroscientists. That touch point on that border, that's where eBrains lives. So, just, in that research, obviously, it's largely been focused, HBP is largely been focused on fundamental research, understanding the brain, mapping out the connectome, mapping out the brain functions, and trying to model that so that it could be simulated or that we can actually replicate parts of the brain. We're not yet at the whole brain, although. Obviously, there's been lots of publications, lots of people working on this. But what is important to say is that we are also here at the pivot point, moving from, let's say, fundamental science to more also translational science. And this is why it's important also to talk to communities like yours, because translating this into the clinical field becomes much more important. A lot of the tools which we have are ready to go there. What is our ambition? That's important, is to make eBrains the reference infrastructure for brain research. It's not a small ambition. We really want to be that solution provider for all different types of communities working on brain data, working on brain science. And we do that through basically enabling this multi-scale research. The brain is a multi-scale organ. If you look at things, you have to go from the molecular level to the whole brain level. So we enable that through our workflows. And basically then we have some of them already, we continue to build on that, is some of these unique tools that help in specific areas of science. Moving on, what are these services? So I can obviously not go in detail, there's 200 of them. So that's not, we've grouped them in 5 different categories, clusters, whatever you name it. And I will touch upon a few of them, just very quickly. So first is data. And here I am at a data conference preaching to the choir about how important data is. I shouldn't be doing that, we all know it. We also know what is the difficulty with data. It exists, but we cannot find it. It exists, but it's not of quality. We don't know what it actually represents. All these problems, I'm not going to say we alleviate them, but we have tools for that. We have a curation system. We have a very state-of-the-art metadata system to actually collect everything that happens with the data. Also very important to the patient organizations that I saw here is we are able to say your data, well, not your data, but the data files that we use have been used in this research. So we're able to actually go back to where it originated and say, you have contributed to this. I think that's important to be able to do that. Although obviously not on an individual level because there's things like GDPR and we know. But this is things we do, and it's not only important for that, I picked out that one, but for scientists to know what happened with that data, what is the quality of it, what do other researchers have to say about it, can I pick up the results of someone else already that worked with this data set so that I don't have to repeat it. All of that is part of our data knowledge service. And as already said, I have also a bit of a background in marketing, so I may be exaggerating here and there a bit. I'm selling things. No, it is there. It is a research platform, so it's not all polished and ready for product, but it is there. Second, most important as well, very linked to the data and actually part of the data service, it is a data service in itself, is the Atlas services we have. When you work on the brain, it's important to know if you have a data file, if you have assembled data, can be MRIs, we talked about feature extraction in MRIs. Where are we actually in that brain? How can we link that? How can we link it to other data? This is where the atlases come in. It is of course very important to be able to visualize these things. That's what the pictures here show. The atlases are based on a very detailed scan of a single brain. Either animals or human brain, and we're further working on that to actually go to very high resolution, but it's a single brain. It's not, of course, all brains. We have tools to actually use that as a reference space, and that's quite important. So that makes data comparable. What are we talking about with this data? Where are we? What's the volume of this type of cell in that region? These kind of things, that's what we have in the Atlas, and that's why it's important. And then very important also for us is simulation. This is a big word, simulation. Actually, I mean, I cannot go into details. Paul will take us definitely a bit further into that. But we actually have simulators across the whole field. I talked about multi-scale. Well, this is where it really shows. There's not one single simulator that captures everything. We go from the molecular level to the whole brain level and anything in between. And it's difficult sometimes to map these different levels because they are working at different time scales, they have different data needs. But this is where another aspect of the platform comes in, something that we're working very hard on, co-simulation, to actually link the different levels so that you can actually, either by data export or by co-simulation, start really seeing details across the whole brain. Simulation, Paul will definitely talk much more about it, so I'll leave that to him. The last one I want to stop on is, I mean, I talked a lot about data, I talked about simulation. The brain doesn't live on its own. It's sitting in a box on top of our body, and the body has an important function, starting with the spinal cord, but actually everything else. So the embodiment is quite important to basically see how that brain functions. But also, of course, there are derived technologies that we have worked on that can make their way into the robotics world for co-robotics and those kind of things. So it's again a bidirectional feed where models go into robotics and we learn new parameters actually from robotics to update the models as well. One thing about this is a very complex thing. If you go there, you will not find your way. I can tell you, even though I shouldn't be saying that. It is complex. There's like 200 services. They all have scientist names, so that means they don't mean anything, the name. But what we do, and this is quite important, is we kind of personalize it towards specific sciences by making workflows, by automating, I should say, certain things that you always need to do. If you take an MRI, then you fall into the pipeline of how do you work with an MRI, the feature extraction, the voxel count, whatever. All of those things will be there, and that's how the tools line up. And all of them are programmatic, accessible, so it's they have UIs, but it's mostly programmatic that this works. So you can attach anything to anything, and that's quite important. That allows us this flexibility, but also by making these workflows, the automation, so that the scientists coming after you can actually benefit from your work. And that takes me then one step further into the next decade. So how do we see this evolving? I've talked about the past, a decade of brain research, so what is the next decade going to bring us? Well, we actually go to we go further with where we are. So basically, we will build these virtual models, but bring them back to reality, constrain them by reality, personalize them with real patient data. And this is where it goes, but actually, we already have a proof point of that, and this is what Paul's going to show us, how actually personalization of such a virtual model, a virtual whole brain simulation, can actually have predictive powers in a certain pathology. So Paul, take it through the details.
Thank you, Steven, and thank you for having me. Thank you for this overview on EBRAINS and also for introducing the concept of a digital twin, because now I will take a deep dive with you into a digital twin for epilepsy, right? Not MS this time, but for epilepsy. But maybe this serves as some kind of an inspiration to do something similar in epilepsy someday. So this is what we call the virtual epileptic patient, with the goal to predict precisely the epileptogenic zones in the brain of patients with drug-resistant focal epilepsy. So this is a severe neurological disorder, and epilepsy in total affects around 1% of the world population. And for these subjects with drug-resistant focal epilepsies, currently the only treatment option is epilepsy surgery, which consists in the removal of the most epileptogenic brain areas. And failures, complete or partial, affect around 40% of the subjects, and particularly in some patients with extratemporal lobe epilepsies. So how does VEP work? Right, VEP, the short, as we call it, for the virtual epileptic patient. So how does it work? Well, it constructs a virtual brain model that is patient-specific, coming from MRI imaging data and electrophysiological data. So for example, we have here a T1-weighted MRI that we used to reconstruct the cortical geometry, the structure of the cortex. We use an atlas to parcellate the cortex into different brain areas. We are using diffusion-weighted MRI to reconstruct white matter fiber bundles and to estimate the connections between brain areas. And we are using, in this case, SEEG data to observe the spatio-temporal dynamics of the individual patient's seizure patterns. This results in such a virtual brain network model where you see these yellow spheres. They are representing individual brain areas, and they are connected by these blue edges as estimated from the diffusion-weighted MRI. And you see we even reconstruct the precise localization of the SEEG contacts coming from post-implantation CT scans in order to accurately map electrical activity at the neural sources onto these sensors. And each of these nodes in the network is equipped with a mathematical dynamical model to represent seizure activity. And now in a simulation of this model, a seizure can start in a particular region and then spread through the network, affecting other areas. And the goal, or what we're doing, is we are matching the simulated seizure activity in the network to the empirical observed patterns. Right? And here we're using statistical methods coming from Bayesian inference, like Markov chain Monte Carlo sampling techniques, in order to estimate the posterior epileptogenicity distribution for each brain area. And so basically what we want to know is which parts of the brain are highly epileptogenic and should be considered for removal, which areas are only the propagation zone, as we call them, so areas that do not seize by themselves but can be triggered by surrounding tissue, and which part of the brain is considered healthy. And this results in the end in such a clinical report that we provide to the clinicians in the pre-surgical staff meeting, which indicates the areas that have been estimated to be highly epileptogenic, together with our confidence in this estimate, and even a heat map on the T1 weighted structural MRI indicating in red these highly epileptogenic areas. And here's on this slide I'm showing an example of a case of a 29-year-old woman with sleep-related hyperkinetic seizures affecting her several times a week, and which so this subject then went under for examination for pre-surgical or for surgical planning. And the pre-surgical MRI revealed possible focal cortical dysplasias in the orbitofrontal cortex. High-density EEG revealed activity in the same area plus something around the insula. So this subject underwent SEEG implantation, which you can see on the right side, and the corresponding time series of recorded seizures on the left. And we see the seizure starts with a polyspike burst followed by low voltage fast discharge activity affecting the orbitofrontal cortex, the anterior and posterior insula, as well as the central operculum. And down in panel C and D, you see the estimation of our VEP workflow. And VEP finds the left insula, the left orbitofrontal cortex, and the left inferior frontal sulcus to be highly epileptogenic, which is also indicated on the structural MRI. And then lastly in panel E, you see the post-surgical MRI. So the subject underwent surgery with a resection of the orbitofrontal cortex and the anterior insula. However, 1 month after surgery, the subject relapsed, again now suffering from nocturnal seizures, however with reduced frequency. And 1 year follow-up now afterwards, the subject is now undergoing again another pre-surgical planning with the intention of possibly removing further parts of the central operculum, which showed activity in the MEG, as well as the left inferior frontal sulcus. So that was an example, but we have tested this method in a retrospective cohort of around 50 subjects, and there we compared the estimations of our model that you see in the middle, coming from data through the VEP pipeline to the VEP estimations, against the clinical hypothesis, so the current state of the art, what the clinicians provided us with the estimation. And we computed different statistics here, most importantly probably for us is precision and recall, and we see for some subjects we have a very good overlap in the estimation of the epileptogenic zones, for other not, which in some sense is expected if you want a new method to provide a different prediction in order to improve some results, then you would see some mismatch in some cases. And we also compared our model prediction to the areas that have been finally resected by surgery. And there, most promisingly, I think we find in panel D on the right side that for subjects that were seizure-free after surgery, there were no false positives predictions by VEP. In other words, all areas that have been estimated to be highly epileptogenic have also been removed by the surgery, and the subject was seizure-free afterwards. So that was quite encouraging, because on the other side, that subjects that were not seizure-free after surgery had some areas still that have been estimated to be highly epileptogenic, still remaining in the brain. They haven't been removed for various reasons. And so that was promising. And of course, a prospective trial would add more validity, or could be another measure to validate of this VEP pipeline. And that's going on right now. It's called the EPINOV trial. We are aiming to include around 400 subjects. And we're currently at 290 subjects included, and there's one control and one intervention group. And for all of these subjects, we get all the data that I mentioned was necessary, and we compute this clinical report, which we provide to the clinicians for the pre-surgical planning. And Of course, we are well aware every method, every model comes with limitations and challenges, and these are a few of them that we are trying to overcome now, also developing further in EBRAINS and the methods and data that is available there. So first of all, with these network-based models, there's only a limited spectrum of possible seizure dynamics that we can simulate. We have a poor resolution or a low resolution of this electrical mapping of electrical activity from neurons, from neural sources to sensors. And we only have limited possibility to integrate all this nice high-resolution data that is becoming available through EBRAINS now. So we do the step from discrete neural masses. On the left side, you see this network of neural masses, which I presented before, to continuous neural fields that you see on the right. So the idea is, instead of having a brain atlas with, for example, 144 regions, each different color on the brain there indicates different regions, they would be collapsed into a single node of the network, right? They would be represented by a single point. And then typically this point would be representative of an area on the unfolded cortex of around 16 square centimeters. Now we are moving to these high-resolution models with around 300,000 vertices. We are using the unfolded cortical surface itself as the structural scaffold for our simulation. And there we are increasing the spatial resolution of our model by a few orders of magnitude, because each point now represents only a surface area of around 1 square millimeter. That gives us the chance to include, for example, high-resolution imaging data coming from the Chenonceau project, which is also available through EBRAINS now. That is a high-resolution post-mortem MRI scan performed at 11.7 Tesla. And together with tractography, this allows us to highly accurately map white matter connections, for example, here showcased for the hippocampus, going into and out of the hippocampus. And we take these fibers as estimated, compute the intersections with the cortical mesh, and we obtain a connectivity matrix, or what we call the connectome of the brain, but now with these 300,000 vertices. And so we have this neural field model that can now simulate completely different dynamics that have been observed in empirical recordings before, but could not be modeled with neural networks or these neural mass-based models. So on the left side, you see the empirical recordings of a real patient with epilepsy. You see these black dots, those are the ECOG. That's the ECOG grid. Each black dot represents one electrode recording local field potentials, and there's one tiny red cross in the middle of the brain that is magnified on the right. That's the microelectrode array, and what you see in later stages of the seizure, you see these traveling wave phenomena, and on the right side you see simulated epilepsy in the insula, which also shows that there's or we can now simulate these traveling waves phenomena as well. But not only on the macroscopic scale we can improve our models, we can also dive deep into the microscopic detailed network models here. Data available in EBRAINS gives us the morphoanatomical features of individual neurons, which then have been positioned using the big brain Jülich database of microscopically detailed images of the hippocampus, in order to reconstruct a model with 4.8 million cells of the CA1 area of the brain. And we use this for something that we call, so we can simulate these models on its own to investigate hypotheses on the microscale. But we can also do something that we call a co-simulation, and we are bridging the scale from micro to macro scale. Stephen already mentioned there are multiple simulators available in EBRAINS. One of them is NEST, which you see on the left side, that is typically used to simulate models on these microscopic detailed levels. And the virtual brain, that is more like the virtual epileptic patient, simulates the full brain with these network models. And now, there are tools implemented in EBRAINS that allow the co-simulation of the two. So we are simulating the full brain, and a part of it, like one specific region of interest to us, that we replace by this microscopic detailed model. And that allows us to actually implement hypotheses about epilepsy pathomechanisms on the microscale and observe at the same time their impact on the spatiotemporal seizure dynamics on the macroscale. And with this slide, I want to close and hand back to Stephen. This slide just gives you an overview of how all these different things are implemented onto EBRAINS. So as a user of EBRAINS, you have this interactive computing environment. We have access, most oftenly we use Jupyter Lab and Python notebooks, but there's other tools as well. And From there, you have APIs like Zebra that allows you to access all these kind of different data. You can access the Atlas services, you can access the knowledge graph, high resolution imaging data. And there's another API called Unicore that allows you to, once you have assembled your high resolution model, you want to run the simulations on any high performance computation cluster. Therefore, you have Unicore to submit these models to run on this high performance computing cluster backend. And with that, I'm handing back to Stephen.
Thank you, Paul. Just a few closing remarks. Yes, I got 4 minutes left, so I can talk a bit. But I don't want to use all the time, so let's maybe open for questions. But I just want a couple of points. So EBRAINS is an official research infrastructure. That's important because it also allows us to actually represent this now as a research infrastructure. We have of course our unique traits. The high data is definitely, this digital data is definitely where we are strong, where we are one of the stronger research infrastructure, and we're building on that. And important to note here is that we talked a lot about science data. This extension towards health data is something we are building now. It is being built. Also very important, whilst I'll skip through a couple of slides, is to say EBRAINS is not finished. So it comes from the Human Brain Project, but it's not finished. We continue to develop on it. Because it's an official research infrastructure, there's also, at this moment, European funds available, but it will have to come through eventually to the member states as any research infrastructure in Europe. But we need to continue to build on it. And that's why these kind of meetings are important, because we need to see where we can bring this. And it's not us that is building these tools on EBRAINS. We are responsible for making sure that it's there, that the infrastructure is there. It's you that have to build these tools and bring the tools and bring the data to these infrastructures. And we are there to really support that. That's important. So we are really moving with EBRAINS towards also not purely this sustainability of tools and data, but actually move to brain health. Another aspect that we are all very obviously very hard working on is upcoming is the neurotechnology field, because that's where the next wave of change is going to come from. Also, when you think about applying pharma to brain, you need positional. You need to position it correctly to have functional impact, and that's where neurotechnology will help. We already see that in the stimulation field today, but that's going to be obviously much more detailed. So together, that will actually help us to build this translational bridge towards the clinical field. And then lastly, I wanted to touch upon something that Lisbeth also touched upon. There is this need for federation. We talk about health data. Health data is not going to move. It is the next few years, even though there's a lot of talks. I'm personally part of the health data space pilot, and we're talking a lot there, but it's not going to change what is there today. Data is in hospitals. We need to be able to work with it. So we already have tools. We have got a medical information platform that's able to federate analysis across hospitals, but it's still complex because it needs to be installed and stuff like that. So we're working on that to see how we can improve that. But again, this has to come with the other side of it. The data has to be made available as well, and that is important. So the incentive to the data holders to actually be able to work with this has to be there. And I'm hoping that with the computational support, with the tools that we bring on top of this platform, that can be extended, that we can actually have that carrot for data holders to say, okay, why don't I enable my data through the research infrastructure? It doesn't have to move, just index it so that we can actually work with it, but you can also work with it. So this is where I want to stop and leave 1 minute for questions. Thank you.